Okay, so now that we've gotten Newton's laws out of the way, we're going to put some applications to them and solve some problems. Okay, so I won't have a lot in this video, but we'll do a lot more in practice. Here I just want to really focus in on setting things up so that you can solve the problems. Okay, so we said that Newton's second law, so second law was F net equals the mass times the acceleration. Remember that net force meant the total forces as a vector sum. So vector sums mean that we include positives and negatives. So if you've got forces going in opposite directions, they would subtract when you combine them. Okay, and we did some stuff in class with this too. So let's review that a little bit. So the quick way to do this would be if I had a box of, say, I don't know, 15 kilograms, and I apply a force in one direction of, I don't know, say 65 newtons, and then say 35 newtons in the other direction. Okay, we can take this, and using Newton's second law, we can determine the acceleration of this object. And we would do that by looking at how much net force acts on the object, which in this case we would have two forces, one at 65, one at 35. So we've got 65 newtons in one direction, and then we have a negative 35 newtons the other direction. So I'm adding the plus sign because, again, net force is total. I add these things up, but if they're in the negative direction, I have to include the negative sign on that number. Okay, the mass itself was 15 kilograms. So if I want to solve this for the acceleration, we simply work out the left side. 65 minus 35 would be 30 newtons equals 15 kilograms times the acceleration. So the acceleration here, divide over the 15, would be 2 meters per second squared. Okay, it's a pretty easy concept when you're doing Newton's second law. Okay, and keep in mind that the net force side, the left side, is up for interpretation. Anything that's applied to the box, you can put on the left side. But just like with vectors, the only thing I can combine is x's and y's, and I have to do them separate. Okay, so that's also important, but we won't do two things going on at once for at least another couple videos. Okay, so that's a pretty easy idea. Now, one of the things we also want to talk about is this idea of weight and gravity. Okay, so let's start off with force due to gravity. So, force due to gravity. Okay, so when we apply gravity to an object, so here we've got, let's just say, a ball, and this ball is falling through the air. Okay, if it's falling through the air, the only force that would act on it is gravity. Okay, so if that's the only force, then we use Newton's second law. The net force equals mass times acceleration. The only force acting on it here is gravity. So we've got the mass times what acceleration? Well, remember, in free fall, the acceleration is downward, and it's the value of the acceleration due to gravity on Earth, which is 9.8 meters per second squared. Okay, so when we're looking at the force due to gravity, we would actually say that the value of that comes from doing mass times the gravity of Earth. Okay, and so keep in mind, though, that G represents gravity on Earth. This number would change depending on the effect of gravity. Okay, and so this defines a force due to gravity for an object, and also to add to this, this is gravity, the force due to gravity when you're near the surface. Okay, if we got really far away from the surface of a planet, the effect of gravity changes, and we would need another set of equations to work that out, and we'll do that in a later chapter. But for now, most objects, for all intents and purposes, they are close to the surface, and so we can say the force due to gravity is simply mg. Okay, so that brings up another idea. Okay, and that's the idea of what is weight versus what is mass. So weight versus mass. Okay, and we want to make sure that we really understand the difference between these two things. Okay, so mass represents the amount of matter contained in an object. Okay, whereas weight, that's not how you spell it. Let's try that again. Where weight is gravity's effect on mass. Okay, but it's a little bit more than that as well. Okay, and so let me give you an example on that. If I have an object and I want to know its weight, okay, the process is fairly simple. We take an object, so say this ball, and we put it on some kind of scale. So imagine that we take the ball and we put it on a bathroom scale. Okay, so what's really going on in terms of forces? So we know that because it has mass, gravity is trying to pull this thing downward. Okay, but at the same time, because it's touching a surface, there's a normal force pushing up on this ball. Okay, now if you don't know how a scale works, typical analog scales, the ones that have a little needle that kind of spin in a circle, they work by looking at springs. So inside this thing there are springs, and as you compress this down, the mechanism inside reads how much the springs are being compressed, and it spits out how much force is pushing down on the scale. So it follows that weight is not necessarily a force. Weight is the result, let's say that, is the result of weighing something. Okay, and I know that definition seems kind of cyclic. Okay, but the idea is I have so much mass, gravity causes me to have a downward force on anything that I touch. If I'm just standing up, then I am exerting a gravitational force down on the floor. Well, I am being pulled by gravity in such a way that I'm exerting a force. But if I were to take my hands, if I'm standing on a scale, and I take my hands and put them on a desk and push myself up, I effectively reduce the amount of force pushing down on that scale. And as a result, my scale reading goes down. It's as if I'm losing weight. Okay, so weight is not an intrinsic value. Weight is a reading that's given to you based on how much force you're pushing down on something else with. Okay, and so that's the main difference between mass and weight. Okay, but if I was looking at this object again, and I did Newton's second law here, so F net equals ma, the net force would be that there's a normal force going up, the gravitational force going down, and the object's not moving. It's at rest on that scale. So that means my net force would have to be 0. So if I solve this for the normal force, and I add the gravitational force to the other side, keep in mind we just did what gravitational force equals. Then we get that the normal force is equal to the force due to gravity of mg. What this effectively means is that the weight of an object at rest is equal to the force due to gravity. Okay, now here's a better example as to how you separate weight from force due to gravity. So again, let's put that ball on the scale, but this time we're going to let both the ball and the scale fall. So the green box represents the bathroom scale, and the red ball represents our mass. And we're trying to weigh the ball. We're trying to figure out how much weight it has. The problem is the ball is falling. We've put it in free fall, and we've also dropped the bathroom scale. So both objects are falling at 9.8 meters per second squared. So what would be the weight of the ball now? Well, since the scale is falling at the same rate that the ball is falling, it follows that there is no longer a normal force, because the scale is not stationary enough to apply a force back up on the ball, because they're both falling. So there's no normal force. And if there's no normal force, there is no scale reading. And if there's no scale reading, then effectively this object becomes weightless. Okay, you're weightless when you're in free fall because there is nothing that can push against you to measure your weight. But it doesn't change the fact that there is still a force of gravity pulling you down with a force of your mass times the gravitational acceleration. Okay, and so that's the main difference. Weight is a reading. Weight is essentially the normal force on a scale. And if you can't get a normal force, then you can't measure a weight. All right, so I mentioned that inside the scale, there is springs. And so we need to know a little bit about how do the springs effectively tell us a force. Okay, so let's talk about a spring force. Okay, so this is known as Hooke's law, and any force that, any spring that obeys Hooke's law has a form that looks something like this. Imagine you had a spring and it was fixed to something. So say we take a spring and we fix it to a wall. Okay, now if I were to take this spring and pull it outwards, so I apply a force to it, okay, I will feel the spring trying to fight back with what we're calling the spring force. So there's a force that fights back called the spring force. Now, how much it fights back with depends on how much we've stretched it from its relaxed length. Okay, so let's say that there's this arbitrary point here. It's called equilibrium, rather when the position is 0, that if I were to let go of the spring, that's how long it effectively is. It would sit against this wall, and it would only be that long. But I take the green force and I pull it out. Okay, and as I pull it away, the further away I get, the harder the spring fights to come back. Think of a rubber band. If you take a rubber band and you try and stretch that thing out, the more you stretch it, the harder it fights back on you. Okay, so that's the idea. And what this guy did, this guy Hooke, is he was able to measure the spring force and gave it a very specific formula. He said the spring force was equal to the negative of what's called the spring constant times how far you've moved from equilibrium. So delta x represents how far from equilibrium. Okay, remember equilibrium was the point where the spring is relaxed. Okay, K represents what's called the spring constant. It's a measure of how stiff a spring can be. So a rubber band doesn't have a great spring constant. You can stretch a rubber band pretty easily. But the shock absorbers on a car, if you try to stretch or compress those springs, it's kind of a pain to do. Okay, so spring constants are just a measure of how strong or stiff a spring is. Okay, now why the negative sign? The negative sign is there because the spring force is always restoring. In other words, when you look at the picture, the yellow spring force is trying to move the object back towards equilibrium. It's trying to restore it back to where it came from. So even if I were to take the spring and compress it inwards from equilibrium, Okay, so same idea. I take this force, call it green, and I compress it in. The spring force is going to try and restore it back to equilibrium. So it's negative because it's always trying to go backwards. It's trying to get it back to that equilibrium point. Okay, and another note about the spring constant. The spring constants are measured in newtons per meter. So how much newtons are needed to stretch this thing per meter? Okay, and that's the idea of a spring force. So one of the ways that you've probably seen a spring force used is in a grocery store, usually in the produce section. Okay, because what you would have is you'd have this basket. Okay, and inside the basket, you put a bunch of fruits or vegetables. Okay, so a bunch of objects sit in the spring. And as a result, what happens is each of these objects exerts a gravitational force downward. So collectively, let's just say it's one gravitational force, which is equal to mass times gravity. Okay, and as it pulls this thing downward, the spring tries to restore it back. Okay, so let's just say, for the sake of this problem, that the spring force, the scale reads that these 5 objects collectively have a weight of 10 newtons. Okay, so if that's the case, how far, and let's say that when we looked at this, we saw that this whole thing, the whole basket, dropped, this whole thing dropped 5 centimeters from its equilibrium. Okay, so we'll ask, what is the spring constant? All right, so if we look at a free body diagram of this, you have the object, you have the spring force pulling up on the object, and you have the gravitational force pulling down on the object. Now, these objects came to rest. So when we set up our net force, right, Newton's second law, we know the net force has to be 0. So we have a spring force minus the force of gravity is equal to 0. The spring force is minus kx, or change in x. Gravity is mg. And we're trying to solve this thing for 0. Or rather, solve it for the spring constant k. So when I go to plug in numbers, I've got minus k. Now delta x in meters. How far did it stretch in meters? 5 centimeters is 0.05 meters. And notice which way it stretched. Downward. Which means our delta x is negative 0.05 meters. The mass of the objects, well, we don't know that, but we know the whole product was 10 newtons. Okay, so if we're trying to solve this for k, we would simply move things over to the other side. All right, so I'm going to go to a new page here. So negative times negative makes positive, so it's 0.05 k is equal to 10 newtons. Oops. So if we divide over the 0.5, our spring constant is right at 200 newtons per meter. Okay, and what's important is this is a constant for the spring. So no matter if we put more objects into this basket or we change the objects, the spring constant doesn't change. Okay, it's a spring constant, and it remains constant for that spring. Now keep in mind that anytime we change this object or change the spring, then we've got to find a new spring constant. Okay, but that's the idea of spring force.